static characterization of titanium 6-4 samples produced by additive manufacturing. So thank you, Matteo, because I don't have to explain what is additive manufacturing. I work with the Laboratoire de Mécanique de Lille, and I have a few co-authors from Thales and the Laboratoire de Mécanique de Lille. So I will start with a little context of the study and the high cycle fatigue results and an analysis of these results, and I will finish with my conclusion. So a short Thales overview, I have to make some advertisement. It's a French electronic company with 61,000 employees, a huge company, present in 56 countries with a revenue of 13 billion euros, shared between defense and cyber. There are 5 main markets: aerospace, space, ground transportation, defense, and security. In all these markets, we have a wide range of products. So they are electronic products, but in these electronic products, we have mechanical parts, such as waveguides, thermal components, structural components, and all these type of components can have an interest for Thales to build them in additive manufacturing. So this is why we are interested in this technology. Here are a few parts built by Thales. So on the top left and top right, these are 2 prototypes, but the one in the middle is a part which is also already in space. So we have many prototypes, but we start to build real parts. And in order to ensure their mechanical properties, I am studying the mechanical performances of additive manufactured parts produced in titanium 6-4. So I study microstructure, static test, and analysis, and I study 3 parameters: the manufacturing orientation, the heat treatment, and the surface smoothness. I use the same technology as Matteo, but I call it differently, SLM instead of SLS, for selective laser melting. In this presentation, I will focus on fatigue tests and on the 3 parameters that I mentioned. So, a little slide on the testing method. We performed some high cycle fatigue tests. So here are the parameters, and we had 5 batches of curved specimens, and we built them in order to evaluate the 3 parameters. So there are some specimens which were built in the z-axis and other in the x-y axis. Some specimens were machined and polished, others were left as built. And some specimens were stress relieved, and others had an HIP heat treatment. And then we compared with casted HIP specimens to compare with the conventional processes. So here are the points. We can see that as built in green is in the lower part of the diagram. Z and XY are in the middle, and in red and orange, and HIP specimens are on the top of the diagram in blue. We compared with the one reference on conventional processes. So we can see that in the X, Y, and Z direction, we are at the level of casting, and after HIP, we are at the level of wrought processes. So it's good result for that. Then I performed some fractographies in order to see on which type of defects the specimens failed. So we had 3 types of defects. The first one is porosity in yellow, so it's often on the subsurface of the specimen. We had also some specimens which failed from surface defects, so it's porosities which are emerging on the surface due to the high roughness. And another type of defects is the unmelted zones. So when the laser had a loss of power or little movement, we can have this type of defects. And they have a different morphology when the specimen is built in the Z direction or in the XY direction. When the layers are differently. So then we analyze the results to see the effect of the parameters. For the casted and high-shaped specimens, we are almost between casting and raw processes. And when we compare with additive manufactured high-shaped specimens, we can see that they are a little bit higher. So it's pretty good for us. Then the effect of the manufacturing direction. So here we can see that the two directions are almost the same fatigue results. And with the three type of defects mentioned earlier, we try to map the results. So at high number of cycles, the specimens almost always fail from porosities. At lower number of cycles, they often fail from unmelted zones, and we can see that dispersion is higher in this zone, and it can be explained by the fact that the geometries and the size of the unmelted zones are very different between the specimens, and implies a higher dispersion. Then we take the effect of the roughness. So again, as-built specimens almost always fail from surface defect due to the high roughness of the surface. It's about 35 microns, as Matthew said. And when we machine the specimens, we get rid of this surface defect, and we have higher fatigue properties. And last, we looked at the effect of the HIP. So here we can see that HIP fed from porosities, but the fatigue properties are higher than not HIP specimens. And this is explained by the fact that the porosities in unmelted zones are often closed defects. So here is an example. It's a sort of closed defect or porosity, and so the defect is very small, and the fatigue properties are higher. When we plot all the specimens together, we can see three zones. So at higher number of cycles, the yellow zones, which are porosities, in the middle the unmelted zones, and on the left the surface defect. And with this we could evaluate three criteria. We could determine three criteria to evaluate the criticality of defects. This is important for Thales to know what we have to control and how we will control them. So the first criteria is the type of defect. So surface defects are more critical than unmelted zones, which are more critical than porosity. Then the size of the defects. Big porosities are more critical. And the position of the defect, the more close to the surface the defect is, the more critical it is. And we can make an analogy with the casting case. So the Langone thesis at the LML he worked on this type of subject on casting and had the same type of conclusions. To finish, so the fatigue tests were performed to evaluate the mechanical properties of additive manufactured specimens in order to build real parts that will be in our products. And additive manufacturing is at least at the level of casting, so it's a good result for us. There is no major anisotropy when small defects are present. Machining and polishing improves the fatigue properties as well as HIP, and the criticality of defects were evaluated with three criteria: the type of defect, the size of defect, and the position of the defects. And in order to confirm or not the hypothesis, I will perform some microtomographic in situ tensile tests, and the results will be available to you. Thank you for your attention.
Thank you. Thank you.